Good morning, students. We are going to see the topic of digital modulation techniques today. As we know that in yesterday class we have concentrated on pulse communication. So, in that we have seen what is the types of pulse modulation we have, what is mean by pulse modulation, and what are the basic steps involved in the pulse modulation and all, and the types of sampling, types of quantization, and the types of modulation like pulse code modulation and differential pulse code modulation. Like that we have seen yesterday. Today we are going to see the digital modulation techniques. Before knowing that a digital modulation techniques, we have to know what is meant by digital modulation. First thing I have to tell you the definition of digital modulation. If the signal is said to be, if we are going to transmit or process a digital message signal, then the modulation is said to be a digital modulation. Whether in this case the carrier may be analog or digital. In general, we have two signals, analog signals and digital signal. If we process the analog message signal through a carrier, then that modulation is said to be analog modulation. If we process a digital signal as a message signal, then the modulation is said to be a digital modulation. This is the simple definition for digital modulation. In general, we can classify the modulation into two types: continuous wave modulation and pulse digital modulation. In this continuous wave modulation, that is simply said to be analog modulation. Analog modulation can be classified into two types: amplitude modulation and angular modulation. And then pulse digital modulation can be divided into two types: digital modulation and analog modulation. Then that angular modulation is divided into two types: frequency modulation and phase modulation. Simply it is said to be FM and PM. In this digital modulation, we have pulse code modulation. Under the pulse code modulation and analog modulation, we have pulse amplitude modulation, pulse duration modulation, and pulse position modulation. Pulse duration modulation is also said to be the pulse width modulation, PWM. The pulse amplitude modulation is simply denoted as PAM. Pulse duration modulation is denoted as PDM, and pulse position modulation is denoted as PPM. Then pulse duration modulation is also said to be the pulse width modulation, PWM. So this is the simple structure regarding about the modulation types. So in major we can say modulation can be divided into two types: analog modulation and digital modulation. Analog modulation in the sense message signal is analog. We are processing analog message signal. Digital modulation in the sense we are processing digital signal as the message. Okay. In analog modulation the carrier should be analog, but in this case of digital modulation the carrier may analog or digital. It's not a mandatory thing, it should be a digital. Okay, then we'll go for next thing, the modulation methods for digital data. How can we modulate our digital data? As I told already, digital data can be modulated by both analog carrier as well as digital carrier. So in this case we have some example. The first one is amplitude modulation, second one is phase modulation, third one is frequency modulation, fourth one is continuous phase modulation, fifth one is trellis coded modulation. Fifth one is trellis coded modulation. Amplitude modulation can be classified as pulse amplitude modulation and quadrature amplitude modulation. Simply it is said to be a QAM. Phase modulation is divided into three types: phase shift keying PSK, a differential phase shift keying DPSK, offset phase shift keying OPSK. Then frequency modulation. Frequency modulation we can say it is a FSK, frequency shift keying method. Continuous phase modulation, Gaussian minimum shift keying GMSK and minimum shift keying MSK. Continuous phase frequency shift keying CPFSK. Trellis coded modulation can be divided into two types: PSK, that is phase shift keying, and quadrature amplitude modulation method. This is the simple example for amplitude modulation, frequency modulation, and digital modulation waveforms. In the first one, we have the amplitude modulation. So, simple concept: the amplitude of the messages varies. In this AM waveform, the third one is the AM waveform, and in this AM waveform, the amplitude of the modulated signal is varies with respect to the message signal. In this case of frequency modulation, the third waveform shows that frequency of the modulated signal is varies with respect to the carriers, with respect to the message signal, with respect to the message signal, that is said to be the frequency modulated waveform. In this case of digital modulation, look at the simple example. We'll have a digital data, that is 10111010. This is our digital data. It simply represent the 1 is represent with the voltage high, 0 is represent with the voltage low. We have only two different amplitude in this digital waveform, whether it may be on or off. Then the carrier is analog here. The carrier is analog. What is the concept here we are following here is, if we are receiving the input signal is 1, we have to represent with high frequency component. We have to represent with high frequency component. If the input data is 0, then it should be represented with low frequency component. How can you identify how high frequency component and low frequency component? If the cycles are very close, then the portion is said to be the high frequency component. The cycle of the signal is far, we can say it is a low frequency component. So by looking this diagram, we can easily identify the first thing is, from this portion to this portion is said to be the high frequency component, and from this portion to this portion is said to be, this portion to this portion is said to be a low frequency component. Low frequency component, it is nothing but a frequency shift keying. This is the example for FSK, frequency shift keying method. A digital input is modulated with the help of analog carrier, then the frequency of the messages vary, then the frequency of the modulated signal is varies with respect to the input digital signal. This method is simply said to be a frequency shift keying method. This is one of the example for digital modulation technique. In a comparison between ASK, FSK and PSK, by the definition, we can easily understand that what is mean by ASK, what is mean by FSK, and what is mean by PSK. So the first thing I have to tell you, ASK, amplitude shift keying. As the name implies, we can say amplitude of the carrier signal is varies with respect to the digital input. Amplitude of the carrier signal is varies with respect to the digital input. That is, now look at this diagram. Here we'll have a digital input, that is 1010. The first waveform is the digital input. The next one is the carrier signal. We are using analog carrier. The next waveform, that is the third waveform, is amplitude shift key, ASK signal. So what is the concept here is amplitude of the carrier. This is the carrier signal, right? The amplitude of the carrier is varies. Look at this portion. Here we'll have the constant amplitude, high amplitude signal. Here we have the low amplitude signal. So the amplitude of the carrier signal is varies with respect to the input message signal. If we are receiving message bit 1 as our input, the amplitude of the output waveform modulated signal is same as like our carrier signal. If we are receiving our input bit is 0, if our input message bit is 0, then the amplitude of the carrier is very less, nearly 0. So we have two variations in the amplitude. of modulated signal. So this is the concept of amplitude shift keying. Simply we can conclude amplitude of the carrier varies with respect to a digital input. With respect to a digital input. Next waveform we have the frequency shift keying as we have seen earlier. So what is the concept of frequency shift keying is frequency frequency of the message carrier signal is varies. Frequency of the carrier signal is varies with respect to the input digital signal. If we receive the input bit as 1, then the modulated signal frequency is high. If we are receiving the input 0, the frequency of our modulated signal is low. So we'll have frequency modulated signal with the constant amplitude. With the have constant amplitude. Here we don't change the amplitude of the carrier signal. Only the frequency of the carrier signal is varies. That will give you the result of frequency shift keying. And then we'll have PSK, that is phase shift keying. Phase of the carrier signal is varies with respect to digital input. With respect to the signal is called digital input. So look at here, if we have the message bit is 1, we don't have any phase shift in a carrier signal. We don't have phase shift in a carrier signal. We'll have 0 degree phase shifted signal as like a carrier. Okay, then input message, that is I received input message is 0. Our carrier signal phases varies by 180 degree. Our carrier signal is carrier signal phases varies by 180 degree. Look at this waveform. We can notice the phase shift, different phases in this waveform. Then what is our next input? 1. So here we should not change the phase of our carrier. So it's same as like a carrier. Then we'll have the input bit as 0. We have to shift our carrier phase by 180 degree. This is said to be the phase shift keying method. So the one of the thing I should tell that in ASK only the amplitude of carrier signal is varies, where frequency and phase of the carrier signal is remains constant. This is the important point we should remember. The amplitude of the carrier is varies, whereas frequency and phase of the carrier remains constant. Frequency and phase of the carrier remains constant. In this case of frequency shift keying, FSK, in this case of frequency shift keying FSK, frequency of the frequency of the carrier signal is varies. The amplitude and phase of the carrier remains constant. But in this case of phase shift keying, frequency and amplitude of the carrier signal remains constant and phase of the carrier signal is varies. So this is the conclusion regarding our amplitude shift keying, frequency shift keying and okay. Next, block diagram of a digital modulation technique. Important thing we should remember. We are getting the problem regarding our BPF band pass filter and pre-coder side. We can get the problem mainly in pre-coder and band pass filter area. So what is the simple concept involved in this structure is we are having a input data, then it will go to process by the precoder. Okay, another input of precoder is our clock signal, and then it will processed by a modulator simply said to be a transmitter. Then what is the another input for modulator is a carrier signal. Here we are going to use your analog signal as a carrier signal. Our input data is a digital signal. So we have to keep it in our mind. Our input data is digital. Our carrier signal is analog. Then it will go to your BPF power amplifier. And then it will transmit over the medium, that is your transmission medium. By In this transmission medium or message, that is a modulated signal is added by the noise or corrected with the noise. And then it will go to a band pass filter power amplifier. Then it will go to a demodulator and decoder circuit. From the band pass BPF power amplifier, that signal will go to a BPF to recover our carrier signal back. Then it will go to a demodulator and a decoder circuit. So in this demodulator, we are deducting our received detecting our original signal back. This is the important structure of digital modulation scheme. Next we will see binary phase shift keying method, BPSK. This is the, simply we can say, this is the type of PSK, that is phase shift keying method. The phase of the carrier is varies with respect to a digital input. What is that the word binary indicates? In the sense, we are having only two phase shift. Only we are having two phase shift. It shows that we can transmit only two different input at a time. Okay, so that's why it is said to be a binary phase shift keying. That's why it is said to be a binary phase shift keying method. Then, how can you define in words? In BPSK, phase of the sinusoidal carrier is changed according to the modulating signal or digital bit to be transmitted. According to the modulated signal or digital bit to be transmitted. A bipolar non-return to zero signal is used to represent the digital data. So I told you that already. A carrier signal phases varies with respect to the modulating signal. That modulating signal is digital. The remaining parameter of the carrier signal, amplitude and frequency of the carrier signal, remains constant. We'll see one example. Here we have taken the input signal as 1010. That input signal is in the form of non-return to zero coding method. That is simply said to be a non-return zero signal. Then we'll have the analog carrier. Then phase of the carrier signal. This is PSK waveform. The third one is PSK waveform. So we have two different input. That is 1, 0. This is nothing but two different input we have. So what is the concept here is, if we are receiving the input bit is 1, if we are receiving the input bit is 1, the phase of the carrier can be varied with 0-degree phase shift. The phase of the carrier signal can be varied with 0-degree phase shift. As simply we can say, we should not change the phase of the carrier. We should not change the phase of the carrier if we receive the input bit as 1. The next thing is, if we receive the input bit as 0, if we receive the input bit as 0, the phase of the carrier is shifted by 180 degree. The phase of the carrier is shifted by 180 degree. So we have only two different phase shift, 0-degree phase shift and 180-degree phase shift. Simple concept. If we receive the information bit is 1, we can use 0-degree phase shifted carrier, or simply we can say um, it is uh, the phase of the carrier remains constant. Then If we receive input bit is 0, we can say our phase shift is the phase of the carrier should be shifted by 180 degree. Phase of the carrier is shifted by 180 degree. Then next slide, bipolar, that is generation of BPSK signal or transmission of BPSK signal. We have the binary data. We'll have a binary data, bipolar non-return to zero level encoder. It will go to a balanced modulator. It will go to a balanced modulator, and then we'll have here in this balanced modulator the another input is carrier generator. Another input is carrier generator. Then it will go to the BPSK, then will generate a binary phase shift signal. Okay, so our input is bipolar non-return to zero level. Our input is bipolar non-return to zero format. Then it will go to a balanced modulator. What is the another input of balanced modulator is carrier signal, analog carrier signal. What is the input of an balanced modulator is analog carrier. So next slide we can say reception of BPSK signal. We are receiving a BPSK signal, that is it will go to a square law device. It will go to a square law device. It will go to a square law device. Then it will go to a band pass filter. It will go to a band pass filter. Then frequency divider. Frequency divider is frequency divider, band pass filter. Then it will go to a frequency divider. BPSK signal is go to a synchronous demodulator. Then it will go to a integrator. It will go to a integrator. Then will go to a decision device. It will go to a decision device. So this is the simplified structure of BPSK receiver. So if we compare with another reception techniques, BPSK is very simple. We'll see the next technique. Next, differential phase shift keying. Differential phase shift keying, DPSK. So the first thing we have seen here, binary phase shift keying. So what is the next method is DPSK, differential phase shift keying. Yesterday also we have seen about DPCM, differential pulse code modulation. Differential pulse code modulation. We have seen a differential pulse code modulation, DPCM. So in that we have taken our input message sequence, and the prediction of the input message sequence also plays a main role to determine the next sample, right? Similarly, in this differential DPSK, difference between the input samples plays the main role here. So we'll have the phase shift gain. The basic form is nothing but a phase shift gain. In that, the basic form is nothing but a phase shift gain. So what is the concept we are going to include here is, what is the concept we are going to include here is, the difference between two successive samples. 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 Um, Successive samples is calculated. What is the definition for um, DPSK is disadvantage in BPSK is complex. Design of carrier recovery by synchronous demodulator. Design of carrier recovery. Design of carrier recovery by synchronous demodulator. Then, to avoid that, DPSK does not need a asynchronous carrier at the demodulator. Asynchronous carrier at the demodulator. DPSK transmitter. DPSK transmitter. Um, DPSK transmitter will have the input data stream D of T. Input data stream D of T is given as one input to XOR gate. Is given as one input to XOR gate. The other input is delayed B of T by time TB uh, by time TB B of T minus TB by time TB B of T minus TB. So look at the diagram. Look at the diagram. So we'll have the transmitter BPSK generation of BPSK signal. So we have the binary data. It will go to a binary bipolar non-return to zero level encoder. That bipolar non-return to zero level signal is going to a balanced modulator. The another input of the balanced modulator is carrier signal. Another input of the balanced modulator is nothing but a carrier signal. Then it will go to the BPSK transmitter. Then we can simply explain by this diagram also. DFT will go to a XOR gate. The delayed input will go to a delay unit. The combination of B of T and B of T minus TB is said to be B of T. The combination of uh, DFT and B of T minus B of T minus TB is said to be a B of T. It is nothing but a balanced modulator. It's said to be a balanced modulator. So what are the digital logic level we have? So we'll have a digital logic level 0. 0 is represented by 0 is represented by the logical value minus 1 volt. What is the input we have is 0, 0, 1, 1. So the 1 is represented by 1 is represented by plus 1 volt, a positive voltage. Um, then V of t minus TB is nothing but another input, that is 0 1 0 1. In the first 0 we can assume that input, we don't know the previous input, like so we are assuming the first input, that's why it is indicated by red mark. uh, and then mm, then logical level, that is 0 B of t can be obtained by using the XOR operation. So D of t and B of t minus TB is XORed. What is the operation of XOR gate is, if we are if the XOR gate receiving the same input, we are getting 0 as the output. If the XOR receiving the different input, we are receiving different we are receiving 1 as the output. Then in this third third input, that is third input is 1 0, so we are receiving the different input, so we are getting 1 as the output. Then what is the fourth one? One is the fourth input is 1 and 1, so we are getting the output as 0. We are getting the output as 0. Uh, Next, this is the waveform of D of t, B of t minus TB. Then we have D of t and B of t minus TB. Then we have the B of t, then B of t. Next we have a DPSK receiver. Here we have B of t in the root of 2 ps cos omega naught t plus theta, omega naught t plus theta. Omega naught t plus theta. Now it will go to a synchronous demodulator multiplier. It will go to a synchronous demodulator multiplier, and then it will go to a delay element. From the modulator, we are receiving to integrator and a bit synchronizer. Integrator and a bit synchronizer. We are getting internet integrator and a bit synchronizer. So like that we have generated DPSK signal. Likewise, we can generate a DPSK signal. Then we have quadrature phase shift keying. We have the quadrature phase shift keying. So QPS, the definition of two successive bits in a stream are combined together to form a message, and each message is represented by a each message is represented by a different value of phase shift of the carrier. So how can we define Quadrature phase shift keying in the sense we have two successive bits can be transmitted over the single channel. Two successive bits in a bit stream are combined together to form a message, and each message is represented by a different value of phase shift of the carrier. So we'll have the two successive bits, whether it may be 0, 0, 0, 0, 1 or 1, 1 or 1, 0. So we'll have the four different inputs. So to represent four different inputs, we are going to use four different phase shift. Here we are using two successive bits, right? So the bit duration can be represented as TS can be represented as 2 bit, that is 2 TP. Then we'll have four different phase shifts. Since four shifts are involved, the system is called as quadrature phase shift keying or 4 PSK system. That is quadrature 4 in the sense, simply we can say it is a quad. So quadrature phase shift keying or a 4 PSK system. If symbol 00 is transmitted at 0 degree, then 01 is transmitted by 190 degree, and 10 symbol is transmitted by 10 is transmitted by 180 degree, and 11 is transmitted by 270 degree respectively. 270 degree respectively. So we can say the typical waveform of the phase shift. So if we receive the 0 as the input, we can say it is a 0 degree phase shifted signal. Then we'll have your 0 1 as their input. Then we can use 90 degree phase shifted signal. Then if we receive 1 0 as the input, we can say it as a 180 degree phase shifted signal. A 180 degree phase shifted signal. If it is a 270 degree phase shifted signal, the waveform will be like this. Next, M array phase shift keying. So we have seen a binary phase shift keying and quadrature phase shift keying so far. Binary phase shift keying in the sense we are going to transmit two different inputs. Then quadrature phase shift keying in the sense we are going to transmit four different input bits. We are going to transmit four different input bits. In this case of M array phase shift keying, we can transmit m number of inputs, whether it may be 2, 4, 8, 16, 32, like that. So if we use, we have to use m number of phase shift for m different input symbols. For m different. So we can say QPSK is a special case of M array PSK, where the phase of the carrier takes on one of m possible values, namely phi m equal to 2m plus 1 of pi by m, where m equal to 0, 1, 2 till m minus 1. The M array PSK signals are obtained as undergroup of n bits together to form n bit symbols. These symbols will extend over a period of n TB, where TB is the bit type. That is 2 power of n equal to m. 2 power of m equal to m. 2 power of m equal to m. Then quadrature amplitude modulation. Next we have the quadrature amplitude modulation. To improve noise immunity of system, uh, to improve to improve the to improve the to improve the noise immunity of system by allowing signal vector to differ not only in their phase but also in an amplitude. Um, uh, to improve noise immunity of system by allowing signal vector by allowing a signal vector by allowing a signal vector to differ not only in their phase but also in amplitude such as system inverse direct modulation of carriers in quadrature. Hence it is called quadrature amplitude modulation. So what is the thing we should remember is here the both amplitude and phase of the carrier is varies. That's why it is said to be a quadrature amplitude modulation technique. Then we have the four different symbols. We show that is n equal to 4 mathematical expression for constellation diagram and 2 power 4 equal to 60 different possible symbols. We can transmit four bits together as a single symbol. So what are the possibilities we'll have is 16 different possibilities we'll have. So it starts from 0000, that is 402. It ends with 4. Then baseband binary data transmission system. Actually, we don't have baseband binary data transmission system in our syllabus. So simply we can intersymbol interference. We have in our syllabus. So what is that ISI, intersymbol interference? As the name implies, it is said to be a kind of interference, a noise or disturbance. So simply we can say if the adjacent symbols are overlapping together, we are getting this kind of noise. The channel with a limited bandwidth is used to transmitting pulse like rectangular pulse. It have to be spread over transmission. This pulse spreading causes overlap of adjacent pulse into adjacent time slots. The signal overlap causes an error at the receiver. The signal overlap causes an error at the receiver. This phenomenon is called intersymbol interference. So simply we can say it is the adjacent overlapping of adjacent samples are said to be the intersymbol interference. The function which produces provides a zero ISC is a sync function by transmitting sync pulse rather than rectangular pulse. This is known as Nyquist pulse shaping. This is nothing but an ideal sync pulse for zero ISI, a frequency response of the filter. The second diagram is nothing but frequency response of the filter. Um, Frequency response of the filter. The next thing we have to remember, Fourier transform of impulse is the rectangular function. In practical, the frequency response of filter is changed with a different role of factor alpha to obtain the achievable filter response curves. Next, we have the DO binary encoding. In general, the bandwidth of communication system depends on the maximum frequency FM in the spectrum of the modulating signal. The bandwidth decreases with reducing FM. The DO binary encoding is a made up of encoding is a mode of encoding a binary bit stream. Thus, if the carrier wave is modulated by DO binary encoder wave, then the bandwidth of the modulated signal will be smaller than if the uncoded data are used. This is the typical eye diagram. Diagram shows here. Here, this is a simple encoder diagram. Then we have uh, partial response signaling also. We'll see in next class. I pattern now. This is another kind of interference. This I pattern is a tool to identify our ISI. Okay, what is that ISI? Intersymbol interference. The distribution of ISI and channel noise in the system can be observed by displaying the received waveform Y of t on an oscilloscope using sweep rate, that is fraction of the symbol rate. The resulting display shape resembles a human eye and it is known as eye pattern of the system. Eye pattern of the system. Interpretation of the eye pattern. Simply By seeing this eye pattern, we can come to know some conclusion that the x-axis with this will tell you the best sampling time. Then margin over noise, we can find out the margin over noise by this length. Then best sampling time, this is our best sampling time. If we take the samples at this time, we didn't get any aliasing at all, then we'll have the sensitivity of the timing error. The slope of the eye pattern will give the sensitivity of the timing error. And then discussion of zero crossings will show the detailed information. Then we'll have equalizer. How can we minimize the ISI? By using the equalizer, we can minimize the ISI. That is one of the important element. To compensate for the channel distortion, a linear filter with adjustable parameters may be employed. The filter parameters are adjusted on the basis of measurements of the channel characteristics. These adjustable filters are called channel equalizers or equalizer. Adaptive equalizer can adjust its coefficients continuously during the transmission of data. Then adaptive equalization for data transmission technique used to minimize signal distortion. So why we go for equalization in the sense to minimize the signal distortion. Equalization is essential for high speed data transmission over the voice grade telephone channel, which is essentially linear and band limited. High-speed data transmission involves two basic operations. What are the operations are discrete pulse amplitude modulation and linear modulation. The amplitudes of successive pulses in a periodic pulse strain are varied in a discrete fashion in accordance with incoming data stream. Discrete fashion in accordance with incoming data stream. Then linear modulation, which offers bandwidth conversation to transmit the encoded pulse strain over the telephone channel. So how can we define linear modulation? Which offers bandwidth conversation to transmit the encoded pulse strain um, over the telephone channel. A pre-channel equalization requires feedback channel cause burden on transmission. It causes some more burden on the transmission. Post-channel equalization achieved prior to data transmission by training the filter with the guidance of a training sequence transmitted through the channel, so as to adjust the filter parameters to optimum values. Adaptive equalization. It consists of trapped delay line filter with a set of delay elements, set of adjustable multipliers connected to the delay line and summa. Coefficients of tapped delay line filter are uploaded using least mean square algorithm, LMS algorithm. Coefficients of tapped delay line filter are updated using a least mean square algorithm. Then input signal x of nt will go to the adaptive equalizer. The output of adaptive equalizer will go to the decision device. That is b of nt will go to the take the another input of training sequence. Two modes of operation: training mode and decision director mode. In this equalizer, we have two different modes of operation. Training mode, a noun sequence D of NT is transmitted and synchronized. This training sequence has maximal length Pn sequence. When the training period is completed, the adaptive equalizer is switched to its second mode of operation. Decision director mode, the error signal equals E of nt equal to B of nt minus Y of nt. Y of nt equalizer output, Y of nt is equalizer output, B of nt is uh, final uh, uh, final correct estimate of the transmitted symbol. Adaptive equalizer operating in a decision directed mode is able to track slow variations in the channel characteristics. Mm, mm. Methods of implementing adaptive equalizer. How can we improve the equalizer in the sense? We can improve analog signal, hardwired digital, programmable digital, analog method, charge coupled devices, CCDs are used. And in this analog method, CCDs are used. CCD FITs are connected in series with the drains capacitively coupled to gates. The set of adjustable tap weights are stored in digital memory locations, and the multiplication of the analog sample values by the digitized tab weights are done in analog manner. Then hardware digital technique. Equalizer input is first sampled and then quantized and stored in shift register. Logic circuits are used for record digital arithmetic operations. Programmable method digital processor is used which provide more flexibility. Time shared to perform a multiplicity of signal processing functions such as filtering, modulation and demodulation in modem. So tapped delay line equalizer. So we'll have the multiple taps. Weights can be adjustable. Weights on the tap are adjusted to get proper desired pulse shape and minimize the ISI. The input and output relationship of tap line equalizer is B of t. Distorted input data Y of B of t is distorted input data. Y of t is filtered output. Cn is weighted of nth filter. Taps increases, accuracy increases. Next we'll see this topic. The first thing is just consider the problem for a BPSK modulator with a carrier frequency of 70 MHz and an input bit rate of 10 Mbps. Determine the maximum upper and lower side frequencies and draw the output spectrum, determine Nyquist bandwidth and calculate the baud rate. Assume FA equal to 5 MHz. So what are the data are given is, I read the question once again. For a BPSK modulator with a carrier frequency of 70 MHz. So the carrier frequency is 70 MHz and the input bit rate is 10 Mbps. Determine the maximum upper and lower side frequencies. Draw the output spectrum. Determine the Nyquist bandwidth and calculate the baud rate. Assume FA equal to 5 MHz. Then, so what are the given data? We have the carrier frequency FC and input bit rate 10 Mbps. Solution substituting these values in the output equation. So what is the output equation is sine of omega at into sine of omega ct, where omega c is nothing but the carrier component and FA is nothing but they are given FA as 5 MHz, right? So how can you substitute in omega? 2 pi f is simply said to be omega. So substitute 2 pi f a into sine of 2 pi f a into sine of 2 pi f c. So sine A, sine B format. So we can say it is cos A minus B minus cos A plus B. We are getting cos A minus B minus cos of A plus B in the format. So upper high frequency minus low frequency is simply said to be the LSB, and USB can be said to be that is message plus carrier frequency. So FC plus FA. So the first component is said to be in this equation. The first component is said to be the LSB, lower sideband frequency. The second one is said to be the upper sideband frequency. So LSF can be calculated by FC minus FM. In this case, they are mentioned as FA. So simply we can say FC minus FA, that is 70 megahertz minus 5 megahertz, that is 65 megahertz. Then we have upper side frequency USF 70 megahertz plus 5 megahertz, that is carrier frequency plus message frequency 75 megahertz. This is LSB. So we can draw the spectrum like this. So we'll have the carrier frequency, that is 70 megahertz, and this is suppressed the carrier. That's why we mentioned as a dotted line. Then USF, that is upper side frequency is 75 megahertz as I have calculated before, and lowest LSF, that is lower side frequency, is nothing but 65 megahertz. Then what is the bandwidth of this spectrum is from LSF to ISF, bandwidth is 10 megahertz. This is the bandwidth of this spectrum. How can you find out the minimum Nyquist bandwidth? Fn equal to some minimum Nyquist bandwidth, that is nothing but the bandwidth which used by this signal is HSF minus LSF. So LSF, so we are getting 10 megahertz. Then the baud rate is FB. FB is nothing but 10 megabar. We are seeing the next example. For a quadrature phase shift keying modulator with an input data rate, with the input data rate FB equal to 10 Mbps and a carrier frequency of 70 megahertz, determine the minimum double side Nyquist bandwidth, Fn, and the baud rate. So for the QPSK signal, they have given input data rate, that is FB equal to 10 Mbps, and carrier frequency FC equal to 70 megahertz. Determine the minimum double-sided Nyquist bandwidth, Fn, and the baud rate. Solution: the bit rate in both I and Q channels is equal to 1/2 of the transmission bit rate, or we can say it is FBQ equal to FB1. The formula is FP by 2. So what is the value of FP? They have given 10 Mbps. So if we divided by 2, we can get 5 Mbps. So we can find out the minimum double-sided Nyquist bandwidth. The highest fundamental frequency presented to either balanced modulator is FA equal to FBQ, that is FBQ is quadrature component, FBI is in-phase component. FBQ divided 2, or we can say it is FBI divided 2. So we can have 5 Mbps divided 2 equal to 2.5 megahertz. Sorry, 2.5 megahertz. The output waveform from each balanced modulator is sine of 2 pi FAT into sine of 2 pi FCT. So we can expand by using cos A minus B minus cos A plus B formula. If we substitute here, we are getting the minimum Nyquist bandwidth Fn equal to HSF minus LSF. So what is the formula? What is the value we have got for HSF is 72.5. LSF is 67.5. So we are getting 5 megahertz is the Nyquist bandwidth. Then the simple rate equals the bandwidth, that is simple rate equal to 5 megabar. Remaining problems will see in the next. As of now, we have seen that the types of digital modulation technique in this class. Simply we can say the definition of the digital modulation, the types of the digital modulation, and shift keying methods. So in detail we have seen that is ASK, yeah, PSK and FSK. In that PSK we have multiple classification method, frequent multiple shift keying method. And that is phase shift keying, binary phase shift keying, frequency shift keying, and ASK amplitude shift keying. In PSK we have seen BPSK, QPSK and DPSK. Then the topic we have covered masked filter, ISI intersymbol interference and equalizer. Then we have seen a problem regarding BPSK and QPSK. We have to continue the problems in next class in digital modulation techniques. That is the shift keying techniques. That is in QPSK, like that we have some problems. We'll discuss in next class. Thank you one and all present here. I have ended this conversation. I have ended this class.